Kolmogorov space. In topology and related branches of mathematics, a topological space X is a T0 space, or Kolmogorov space named after Andrey Kolmogorov, if for every pair of distinct points of X, at least one of them has a neighborhood not containing the other. In a T0 space, all points are topologically distinguishable. This condition, called the T0 condition, is the weakest of the separation axioms. Nearly all topological spaces normally studied in mathematics are T0 spaces. In particular, all tone spaces, i.e. all spaces in which for every pair of distinct points each has a neighborhood not containing the other, are T0 spaces. This includes all T2 or Hausdorff spaces, i.e. all topological spaces in which distinct points have disjoint neighborhoods. In another direction, every sober space which may not be tone is T0. This includes the underlying topological space of any scheme. Given any topological space, one can construct a T0 space by identifying topologically indistinguishable points. T0 spaces that are not tone spaces are exactly those spaces for which the specialization preorder is a non-trivial partial order. Such spaces naturally occur in computer science, specifically in denotational semantics. Definition and definition. Examples and counterexamples. Nearly all topological spaces normally studied in mathematics are T0. In particular, all Hausdorff T2 spaces, tone spaces and sober spaces are T0. Spaces which are not T0. A set with more than one element with the trivial topology. No points are distinguishable. The set R2 where the open sets are the Cartesian product of an open set in R and R itself, i.e. the product topology of R with the usual topology and R with the trivial topology, points A, B, and A, C are not distinguishable. The space of all measurable functions f from the real line R to the complex plane C such that the Lebesgue integral of fx2 over the entire real line is finite. Two functions which are equal almost everywhere are indistinguishable. See also below. Spaces which are T0 but not tone. The Zariski topology on spec R. The prime spectrum of a commutative ring R is always T0, but generally not tone. The non-closed points correspond to prime ideals which are not maximal. They are important to the understanding of schemes. The particular point topology on any set with at least two elements is T0, but not tone since the particular point is not closed. Its closure is the whole space. An important special case is the Sierpinski space, which is the particular point topology on the set 1. The excluded point topology on any set with at least two elements is T0 but not tone. The only closed point is the excluded point. The Alexandrov topology on a partially ordered set is T0, but will not be tone unless the order is discrete agrees with equality. Every finite T0 space is of this type. This also includes the particular point and excluded point topologies as special cases. The right order topology on a totally ordered set is a related example. The overlapping interval topology is similar to the particular point topology since every open set includes 0. Quite generally, a topological space X will be T0 if and only if the specialization preorder on X is a partial order. However, X will be tone if and only if the order is discrete, i.e. agrees with equality. So a space will be T0 but not tone if and only if the specialization preorder on X is a non-discrete partial order. Operating with T0 spaces. Examples of topological space typically studied are T0. Indeed, when mathematicians in many fields, notably analysis, naturally run across non-T0 spaces, they usually replace them with T0 spaces in a manner to be described below. To motivate the ideas involved, consider a well-known example. The space L2 R is meant to be the space of all measurable functions f from the real line R to the complex plane C such that the Lebesgue integral of fx2 over the entire real line is finite. This space should become a normed vector space by defining the norm f to be the square root of that integral. The problem is that this is not really a norm, only a seminorm, because there are functions other than the zero function whose seminorms are zero. The standard solution is to define L2R to be a set of equivalence classes of functions instead of a set of functions directly. This constructs a quotient space of the original seminormed vector space, and this quotient is a normed vector space. It inherits several convenient properties from the seminormed space, see below. In general, when dealing with a fixed topology T on a set X, it is helpful if that topology is T0. On the other hand, when X is fixed but T is allowed to vary within certain boundaries, to force T to be T0 may be inconvenient since non-T0 topologies are often important special cases. Thus, it can be important to understand both T0 and non-T0 versions of the various conditions that can be placed on a topological space. The Kolmogorov quotient. Topological indistinguishability of points is an equivalence relation. No matter what topological space X might be to begin with, the quotient space under this equivalence relation is always T0. This quotient space is called the Kolmogorov quotient of X, which we will denote KQX. Of course, if X was T0 to begin with, then KQX and X are naturally homeomorphic. Categorically, Kolmogorov spaces are a reflective subcategory of topological spaces, and the Kolmogorov quotient is the reflector. Topological spaces X and Y are Kolmogorov equivalent when their Kolmogorov quotients are homeomorphic. Many properties of topological spaces are preserved by this equivalence. That is, if X and Y are Kolmogorov equivalent, then X has such a property if and only if Y does. On the other hand, most of the other properties of topological spaces imply T0-ness. That is, if X has such a property, then X must be T0. Only a few properties, such as being an indiscrete space, are exceptions to this rule of thumb. Even better, many structures defined on topological spaces can be transferred between X and KQX. The result is that, if you have a non-T0 topological space with a certain structure or property, then you can usually form a T0 space with the same structures and properties by taking the Kolmogorov quotient. The example of L2R displays these features. From the point of view of topology, the seminormed vector space that we started with has a lot of extra structure. For example, it is a vector space and it has a seminorm, and these define a pseudometric and a uniform structure that are compatible with the topology. Also, there are several properties of these structures. For example, the seminorm satisfies the parallelogram identity, and the uniform structure is complete. The space is not T0 since any two functions in L2 or that are equal almost everywhere are indistinguishable with this topology. When we form the Kolmogorov quotient, the actual L2R, these structures and properties are preserved. Thus, L2R is also a complete seminormed vector space satisfying the parallelogram identity. But we actually get a bit more, since the space is now T0. A seminorm is a norm if and only if the underlying topology is T0, so L2R is actually a complete normed vector space satisfying the parallelogram identity, otherwise known as a Hilbert space. And it is a Hilbert space that mathematicians and physicists in quantum mechanics generally want to study. Note that the notation L2R usually denotes the Kolmogorov quotient, the set of equivalence classes of square integrable functions that differ on sets of measure 0, rather than simply the vector space of square integrable functions that the notation suggests. Removing T0. Although norms were historically defined first, people came up with the definition of seminorm as well, which is a sort of non-T0 version of a norm. In general, it is possible to define non-T0 versions of both properties and structures of topological spaces. First, consider a property of topological spaces, such as being Hausdorff. One can then define another property of topological spaces by defining the space X to satisfy the property if and only if the Kolmogorov quotient KQX is Hausdorff. This is a sensible, albeit less famous, property in this case. Such a space X is called preregular. There even turns out to be a more direct definition of preregularity. Now consider a structure that can be placed on topological spaces, such as a metric. We can define a new structure on topological spaces by letting an example of the structure on X be simply a metric on KQX. This is a sensible structure on X. It is a pseudometric. Again, there is a more direct definition of pseudometric. In this way, there is a natural way to remove T0-ness from the requirements for a property or structure. It is generally easier to study spaces that are T0, but it may also be easier to allow structures that aren't T0 to get a fuller picture. The T0 requirement can be added or removed arbitrarily using the concept of Kolmogorov quotient.